Hi boys and girls, this is lecture 4.7 in unit 4. The topic, optimization problems. This is part 2 of our lecture regarding this topic. In this lecture, I'm simply going to do a few more optimization problem examples, but I thought I would start with reminding you of the guidelines for solving applied minimum and maximum problems. Identify all given quantities and quantities to be determined. If possible, make a sketch. For sure, make a sketch. I can't imagine a scenario in which a sketch would not be a good idea. Write a primary equation for the quantity that is to be maximized or minimized. Then reduce the primary equation to one having a single independent variable. Remember, you're usually using an equation that is some standard geometric equation for area or perimeter or volume, and most of the times those formulas have more than one variable. There's more than one dimension involved. There might be length and width or radius and height. But for you to be able to take the first derivative of your primary equation, it needs to have only one independent variable. That means, of course, that we would need to use a secondary equation, which relates the same variables that the primary one does, but you'll use the secondary equation to solve for one variable in terms of the other, so that you'll be able to replace one of the variables in the primary equation with that substituted value, resulting in a primary equation which has one independent variable. Then we would determine a feasible domain for the primary equation, what values make sense for the problem, and then determine the desired maximum or minimum value by using the first derivative. So let's do a few more examples. In this example, we're going to minimize fencing. A 384 square meter plot of land is to be enclosed by a fence and divided into two equal parts by another fence parallel to one pair of the sides. So this is the scenario that we have. Here's the plot of land, the outer fencing, but an additional fence has been added to divide the plot of land into two pens rather than one. What dimensions of the outer rectangle will minimize the amount of fence used? Now, we see that we're going to be minimizing fencing, which of course is a perimeter formula. But it's not just the perimeter of a standard rectangle because we've added this additional fence. So as I've stated before, sometimes the equation that you're going to be minimizing or maximizing needs a little bit of tweaking depending on the scenario, and that's what we have here. So as we set up this equation, let's label the short side of this rectangle X. But of course that means we have three lengths of fencing that are that length. And then we'll label the long side of the rectangle Y. So the equation that we want to minimize, which represents the amount of fence that's going to be used for these two pens, is 3x plus 2y. Now, of course, as usual, we have more than one independent variable in our primary equation, so we need to set up a secondary equation in order to eliminate one of these variables. Fortunately, they give us the area of this plot of land. Now, remember, the area is not affected by the additional fencing in the middle. The area is still just going to be length times width here. And since we know what the area is, we can say 384 equals xy and solve for one of these variables in terms of the other. It doesn't really matter which one we solve for. I'm going to solve for y and let this be 384 over x. Now we take this quantity, this expression, and we go replace the variable in our primary equation with that quantity, giving us a new primary equation that now is reduced to one independent variable, 3x plus 2 times 384 over x. Let's simplify this a little bit before we take the first derivative. 3x and 2 times 384 is 786. No, sorry, it's 768. Doing that in my head. 768 x to the negative 1, bringing the variable up to use the power rule. So now, let me just double check as I was doing that multiplication. 8, 16, got it. All right. So let's change color and take the first derivative. P prime is going to be 3 minus 768x to the negative 2. We know that we'll get maximum and minimum values by setting our first derivative equal to 0. So this will be 0 equals 3 minus 768 over x squared. Now let's add this term over to the other side. This will give us 768 over x squared equals 3. When we multiply both sides by x squared, we'll get 3x squared equals 768. Dividing both sides by 3 gives us x squared equals 256. Take the square root of both sides, and of course we neglect the negative root here. We'll get x equals 16. Therefore, to minimize the amount of fencing being used with this particular situation, you need to let x be 16. Remember that we need the dimensions of the outer rectangle to answer the question, so we also need to know what y is. Since 384 is xy, we'll replace x with 16 and divide both sides by 16. It turns out that y will need to be 24. And there we have the dimensions of the outer rectangle in order to minimize the amount of fencing being used. In this case, our units will be meters. So make sure you label each dimension with the units for your final answer. In this example, we're going to minimize the material needed to make a cylindrical soda can. What is the radius of a cylindrical soda can with volume of 512 cubic inches that will use the minimum material? To minimize material of a right circular cylinder, we're going to need the equation for surface area of a right circular cylinder. Now, even though I have this nice little screenshot of a soda can here, our cylinder is actually just a straight right circular cylinder. It doesn't actually have these little beveled edges and, the details that we see here. So the two dimensions that we use in a right circular cylinder are radius and height. So let's remember what the surface area of a right circular cylinder is. It's going to be the area of the top and the bottom, which are two circles, thus 2 pi r squared, plus the lateral area of the can, which can be found by taking the circumference of the circle times the height. So that will be 2 pi r h. Now remember that pi is a constant. So the two variables that I have here are radius and height. Of course, 2 is too many variables to have in our primary equation, so we're going to need to reduce this equation to one independent variable. Thus, we will use the other information that we were given in the problem to do so. The volume of this can is 512 cubic inches, and the volume of a right circular cylinder is the area of the base times the height. So that will be pi r squared h. We were told what the volume was. It's 512 equals pi r squared h, and we can easily solve for h here by dividing both sides by pi r squared. And this results in an expression for h that we can now plug into our primary equation, replacing the variable there, and that's what we're going to do. So we're going to take that expression, rewrite our surface area equation, 2 pi r squared plus 2 pi r, and then of course instead of h, we'll put 512 over pi r squared. Now let's do a little bit of simplification. The pi's will cancel. The r is going to cancel with one of the r's in the denominator, just leaving one. And if I rewrite this, I'm going to have surface area then will be 2 pi r squared plus 2 times 512 is 1024, and this will be 1024 over r, but I'm going to write this, of course, as r to the negative 1 so that I can use the power rule when I take the derivative. So let's take the derivative of our surface area equation. I'll put this in parentheses just because it's 2 letters instead of 1. The derivative of surface area then is going to be, remember this is the only variable, the derivative of r squared is 2r, so this becomes 4 pi r, and then negative 1 times 1024 gives me negative 1024 r to the negative 2. There's the first derivative. Let's set it equal to 0 and find where our max and min radius might be. Max or min radius. In this case, of course, we're hoping for a minimum. Now I'm going to rewrite this as 1024 over r squared, and when I add that term over to the other side, I get 1024 over r squared equals 4 pi r. Multiplying both sides by r squared leads me to 1024 equals 4 pi r cubed. Now let's solve for r cubed by dividing both sides by 4 pi. This gives me r cubed equals 81.407. No nice little integers here for us. We're just going to have to deal with the decimal approximation. And then when I take the cubed root of 81.487, oops, that was supposed to be an arrow, r is equal to 4.355. 4.335, I'm sorry. And in this case, that will be inches. Now, in this problem, we were asked to just find the radius, which will use the radius of the cylinder with that volume that will use the minimum amount of material. Therefore, we don't have to go back and solve for h, although we could do so if we wanted to. And that's your answer. In this last example, we're going to find maximum area. A rectangle with sides parallel to the coordinate axes is placed as shown within the curves of y equals the square root of x, the vertical line x equals a, and the vertical line x equals 9, and the horizontal line y equals 0, which is just the x-axis. Find the dimensions of the rectangle having the maximum area. So we're going to come up with an area formula for this rectangle, take the derivative in order to find the maximum area, or find the dimensions which would yield the maximum area. Now notice we don't exactly know what A is. I just placed it here to represent the unknown quantity that we're going to find, but we do need to determine what the dimensions of this rectangle would be in our primary equation, which of course will be an area equation. The area of a rectangle is length times width. What is the length of this rectangle? Well, you can see that it's going to be the distance to 9 minus the distance to A. What is left there, of course, is the length 9 minus A. Now you can see that the height of this rectangle is going to be the function value on the curve at A. Well, we do have a secondary equation here. It's just the function equation for this curve. So we can say, using this function, we can say that the height of this rectangle is going to be the square root of A. If we were able to plug A into the function and get that function value, we know that that would be the height of our rectangle. So using the secondary equation, we were able to come up with the two dimensions that we need using only one variable. So this is going to be the square root of A times 9 minus A. The height times the length, or the width times the length. Now let's rewrite this as A to the 1/2 times 9 minus A, and distribute that A to the 1/2. We'll have 9A to the 1/2 minus A to the 3/2. Now we're ready to take the first derivative. A prime will be 9/2 A to the negative 1/2 minus 3/2 A to the positive 1/2. 3/2 minus 1 is 1/2. Now we know that we'll get max or min dimensions here for A by setting this equal to 0. And I am going to factor out a couple of quantities here. I'm going to factor out the 1/2 because I know this needs to drop to the denominator of my expression. And I'm also going to factor out the smaller of the variable quantities, which is A to the negative 1/2. So when I take out 1/2 A to the negative 1/2, what I'm left with from this first term is just 9. In my second term, I'm left with minus 3. Remember, when I take out A to the negative 1/2, it's as if I'm dividing this variable by A to the negative 1/2, so I need to subtract the exponents. 1/2 minus a negative 1/2 is 1. So this is now A to the 1. Now let me simplify a bit further. We're going to have 9 minus 3A over 2A to the 1/2. Remember that your critical numbers will come from setting the first derivative equal to 0 and also determining where the first derivative is undefined. So first we'll set the numerator equal to 0. 0 equals 9 minus 3a. That means 3a equals 9, which means a equals 3. However, we can also see that the denominator is undefined at a equals 0. So here's another potential place where a max or min might occur. Let's talk about what would happen if a was 0. If a were 0, then the length of your rectangle would be 9, but the height of your rectangle would be the square root of 0, which is 0. You would end up with an area which is 0. That means 0 will yield the minimum area of 0. And that, of course, is not what we're looking for. So let's try 3. We know that 3 is not going to yield the minimum area. We already know what yields that. So 3 is going to yield the maximum area. That means that our dimensions of this rectangle should be 9 minus a, which is 3. That will be a length of 6. And then, of course, the square root of 3 will be your width. So this is going to be the square root of 3 by 6. Those are the dimensions of the rectangle with maximum area given the constraints given here. That's it for today's lecture. I wonder how the honeybee knew that a hexagon was the best shape to use to minimize material and maximize volume. Great is our Lord and mighty in power. His understanding is infinite. Psalm 147:5. God bless you, boys and girls.